Hi there! Today we will explain what semiconductors are, and then we will take a look at the diode, one of the simplest devices that can be built out of a semiconductor. Let's dive in, but before that, please take a minute to subscribe to this channel if you like it, and consider becoming a patron. Links are in the description below. The primary elements that allow us today to build electronic devices are so-called semiconductors. A semiconductor is an element that has some characteristics of an insulator, but also some characteristics of a metal. In fact, in chemistry they are actually called semi-metals. In their most pure state, they behave like an insulator, but when they are heated or when impurities are introduced in their crystal structure, they start to behave like a conductor of some sort. If you are not familiar with the concept of conductors, insulators and semiconductors, I suggest you to go look also at my video on this subject. Link is here in the upper right corner of your screen. You can also take a look at my article on eleneasy.com written back in July 2019. I posted a link to it in the summary below. A pure semiconductor, like silicon and germanium, has a tetrahedral crystalline structure or lattice, where each atom is connected to 4 more atoms at the vertices of the tetrahedron. Here is a view of a single tetrahedron structure. You can see clearly how the atom in the center is connected to the other 4 at the vertices of the tetrahedron. This formation extends in all 3 directions of space, each time adding new atoms that take part in this ordered structure. Let's take a look at this 3D rendering of the lattice. Do you see how each tetrahedron is connected to the other tetrahedrons, keeping an ordered structure that goes on and on in all directions? Look also how the view changes just by rotating the structure. In one direction it looks like an endless series of hexagons, while in this other direction it looks like a series of squares. This side view, actually, is the one where we can best see each atom connecting with the 4 others, almost on the same plane. It is the peculiarity of this view that allows us to simplify the rest of this discussion, examining the atoms exactly like that, like they are all ordered on the same plane, and each group of 4 is distributed at the vertices of squares. This is also the reason why this kind of lattice is actually defined as a diamond cubic structure, since this is actually the same structure as a diamond that is made of carbon atoms. It is only fair to say that I am about to give a simplified explanation of what is going on, but for the sake of this discussion, this is enough for understanding what semiconductors are and how they behave. If you are interested in more details about the lattice structures of semiconductors, I have left for you a few links on the description below that you may find interesting. The diamond cubic structure, obtained by the mutual connection of smaller tetrahedral elements, is typical of all the elements of the 4th group in the periodic table. Each bond between one atom and an adjacent one is a covalent bond, where each atom shares one electron with each adjacent one. A structure like this completes the octet of electrons in the valence band of the atom, and therefore it is very stable and, in appropriate temperature conditions, behaves like an insulator. However, germanium and silicon need a relatively low energy to move one of these electrons from the valence band to the conduction band. This is easy to do just by providing some heat to the crystal, or a strong enough difference of potential. Once the electron is in the conduction band, it is free to move within the boundaries of the lattice, not forced anymore to stay close to its atom. When that happens, we say that it leaves behind a so-called hole. The electron is negatively charged, and when it leaves a hole behind, the atom to which it belonged remains unbalanced, and therefore with a positive charge equal in absolute value to the one of the electron. In other words, by providing energy to the crystal, we create pairs of electrons and holes. When an electron moving in the lattice happens to pass close to a hole, left behind by another electron, it is attracted by the positive charge and fills the hole left by the other electron. We say that the electron has moved, creating a negative current in one direction, while a hole has moved in the opposite direction, creating a positive current. But since the movement of both electrons and holes is totally random, the overall average current flowing in the lattice is zero, unless of course we reduce or remove the randomness by applying a voltage at the ends of the barrel semiconductor. In order to facilitate the conduction of current in a semiconductor, we inject some impurities in the lattice, using an element in an adjacent group in the periodic table. This technique is called doping. We basically dope the semiconductor to make it behave differently than it would normally do. Here is how. Let's concentrate on silicon for now, with the understanding that what we will say works exactly also for germanium. There is a number of other substances used as a semiconductor, of course, but those are compounds made of several elements put together that mimic what an actual doped semiconductor does. Usually, these compounds are used for very specific reasons, to enhance peculiarity observed in elemental semiconductors, for example, and use it in a very specific niche of electronics. So let's consider a 2D representation of one layer of the silicon lattice. In its pure state, and within certain temperatures, this structure is very stable and all the electrons of the valence band provide the covalent bonds to keep the structure together. In this situation, there are no charges moving around, and so the resistance of a piece of silicon like that is high. If we connect the two ends of a bar made of such pure silicon with a small battery, no current is created. Increasing the voltage of the battery may however inject enough energy in the bar that some electrons are able to jump in the conduction band, and therefore we will have a current flowing through this circuit. Similar thing would happen if we increase instead the temperature of the bar. But now, let's add to the lattice a few atoms of an element in the fifth group of the periodic table, for example, arsenic. When we do so, the arsenic atoms will replace some atoms of silicon in the lattice. However, arsenic has 5 electrons in its valence band, not 4 like the silicon. As a result, 4 of the electrons in the arsenic atoms will create similar covalent bonds as the silicon atoms that have been replaced, but for each arsenic atom there will be one further electron that is not bonded with anything. As a result, these extra electrons remain free to move inside the lattice. When we dope a semiconductor this way, we obtain what is called an N-type semiconductor, to highlight the fact that now there are free-to-move negative charges in the lattice. Note, however, that the doped semiconductor has still an overall charge of 0, because the charge of the free electrons is balanced by the extra positive charges that the arsenic nuclei have with respect to the silicon. If we now apply a voltage at the two ends of such a semiconductor, there will be a flow of current due to these free-to-move electrons, even if no pair of electrons and holes are created. Let's now look at a different case of doping, this time done with an element in the third group of the periodic table, for example boron. Boron has only 3 electrons in its valence band, and so, when it replaces an atom of silicon in the lattice, it can only establish 3 covalent bonds with the adjacent silicon atoms. The 4th bond will be missing an electron. We have created a hole in the crystalline structure, and because there is a missing electron, we have in fact a local positive charge that is not balanced by any electron. We express this by saying that the hole carries a positive charge. Replace a number of silicon atoms with an equal number of boron atoms, and now we have a number of positively charged holes in the lattice. We highlight this by saying that now we have a p-type semiconductor. However, again, the total number of charge is still 0, because holes are generated by boron atoms that have a smaller positive charge than silicon in their nuclei. Now, if we apply a voltage to a piece of such p-type semiconductor, something very peculiar happens. With just a little energy provided by the battery, and helped by a whole positive charge close by, an electron from a covalent bond can abandon its position and go fill the hole that was left by the boron. Doing so, it leaves behind another hole. Looking at high level, it is like the hole has moved from one position to another, toward the negative of the voltage applied to the bar. Do this for several holes, and now we have an actual current made of holes, which behave like positive charges moving away from the positive of the battery and going toward its negative. We have created a current made of positive charges inside the p-type semiconductor. Isn't that cool? You see, that's one of the reasons why we normally define a conventional direction of the current when we solve circuits. We always say that the conventional current flows from the positive to the negative, and we don't have to worry that actually the current can and will flow in certain components in one direction or the other, depending on the available charges being positive or negative. But let's get back to our subject. Let's consider now 2 bars. one of type P semiconductor on the left and one of type N semiconductor on the right. And now let's move them close until they touch each other. In the vicinity of the touching surface, we have on one side an excess of holes, while on the other side there is an excess of electrons. Since both kinds of charges are capable of moving inside the lattice, it happens that the electrons on the right are attracted by the positive charges on the left side, and so they move toward the left. At the same time, the holes on the left side are attracted by the electrons' negative charge on the right side, and so they start moving toward that side. There will be a region close to the surface of contact, which we usually call junction, where the electrons and the holes will find each other and therefore the electrons will start filling the holes, so that the charges will start neutralizing each other. This central region will then become neutral, with no charges of any kind. And this process will continue for a while, and the central region will start to expand until the moment where the electrostatic field between the two bars will be such that it will not make possible for any further charge to move to the other side. The final result is an area around the contact region, the junction, that is completely emptied of charges. It will be like the two plates of a capacitor, where all the charges are on the left and on the right, and nothing in between. A device built like this is called a solid-state diode. It is called diode because it mimics the same functionality as the old thermionic tubes called diodes. It is solid state because it is made out of a solid crystal, while tubes used to carry a current worked in the vacuum. Let's now see how it works. Let's start by applying a voltage with the negative on the P side and the positive on the N side. The negative voltage will start attracting more holes toward its electrode. At the same time, at the other end of the PN bar, more electrons will move toward the positive electrode. As a result, the neutral region of the boundary between the P and the N semiconductors will expand further, preventing any current from flowing. We call this the reverse bias of the diode, and its result is that no current will flow through the circuit. But if we now reverse the voltage by applying the positive to the P side and the negative to the N side, the opposite will happen. Electrons will be pushed away from the negative terminal and the holes will be pushed away from the positive terminal. As a result, the neutral gap around the PN junction will start closing. And when the voltage exceeds about 0.6 volt, the gap will close entirely. At that point, electrons will start moving from the N semiconductor to the P semiconductor, and at the same time, holes will move from the P semiconductor to the N. The moment they reach the junction, the electrons will start filling the holes, neutralizing all the charges. But now, the battery used to provide the voltage will start injecting new electrons in the N-type semiconductor to compensate for those that fill the holes in the center, and the electrons, repelled by the negative voltage of the battery, will start moving toward the junction. At the same time, the same battery will start removing electrons from the P-type semiconductor, creating new holes that will start traveling toward the junction. And so, as long as the battery is there, we will end up having a continuous flow of holes going from the positive terminal to the contact area, and a continuous flow of electrons from the negative terminal to the contact area. In other words, an electric current. Outside the semiconductor, instead, we will have a continuous flow of only electrons that leave the P semiconductor, enter the positive of the battery, exit from the negative of the battery, and enter again the diode through the N semiconductor. Again a current, but this time made only of electrons. We call this the forward bias of the diode, and its result is a current flowing through the whole circuit, keeping continuously a balance between the number of electrons that enter the diode from one side and the number of electrons that leave the semiconductor from the other side. For analogy with a vacuum tube called a diode, which behaves exactly the same way with forward and reverse bias, we name the electrodes of this solid-state diode anode and cathode, where the anode is the one that needs to be polarized by the positive voltage to conduct the current, and the cathode is the one that needs to be polarized by the negative voltage. And finally, here is the symbol used in the schematics to indicate a diode. The vertical bar represents the cathode, while the arrow represents the conventional direction of the current when the diode is forward biased. If we represent this behavior on a graph, where the horizontal axis is the voltage and the vertical axis is the current, the ideal diode will have the following shape. If we consider that to start the conduction with a forward bias we need to exceed a certain threshold, which we have said to be about 0.6 volts for silicon diodes, the graph would be like this. In reality, however, the current does not increase indefinitely when we reach that voltage threshold. Instead, due to the intrinsic resistance of the silicon, it will be more like this. And this is still not the actual characteristic of the diode, because the resistance is not really a constant for such a component, but instead diminishes with the increase of the bias voltage. So the actual characteristic of a diode is more like this. The voltage Vd, at which the diode starts conducing current, is usually called forward voltage or knee voltage or cut-in voltage, and that is the voltage where the neutral gap at the PN junction closes entirely, allowing the current to flow. The diode we have described so far is the one called a rectification diode, or rectifier, and is widely used to convert an alternate current into a direct current, or an AC into a DC. However, there are several other kinds of diodes used for an even greater number of applications. Let's take a quick look at some of them. The small signal diode. It is basically the same as a rectification diode, but it is doped in such a way that presents a smaller forward voltage and conversely cannot support elevated currents. Such a diode is used to process small signals, from which the name, like when we want to extract a modulating signal from a carrier, for example in the AM radio receivers. I have used such a diode also in my Theremin project to extract the audio signal in the heterodyne mixer. The Schottky diode. This diode uses a metal semiconductor junction instead of a PN junction. This allows to build a diode that has a smaller neutral gap at the junction, which reduces the internal capacitance and increases the switching speed, which measures how fast the diode can switch from forward to reverse bias. These kind of diodes are used everywhere there is a need to have diodes that switch very fast and that have a very small parasitic capacitance. They are very useful in high-frequency circuits. Nowadays, they are also used as fast rectifiers, which helps to reduce the ripple in power supplies. The Zener diode. Zener diodes are made of a PN junction, like the rectifiers. But the doping of these diodes is much more intense and is calculated in such a way that they can conduct current also when reverse biased, but only when we exceed a very specific reverse voltage applied to them. Their characteristic is like this. When forward biased, they behave like a normal diode. When reverse biased and the voltage exceeds a predetermined value, they are affected by a phenomenon called the Zener effect. The Zener effect manifests in these diodes when they are designed with a breakdown voltage of 5 to 6 volts or less. This breakdown causes the diode to suddenly start conducing a lot of current, which we can limit using a series resistor. Zener diodes are normally used as voltage regulators. The avalanche diode. These diodes behave similarly to the Zener diodes, and because of that they are erroneously called Zener diodes themselves. In reality, these diodes are designed to have breakdown voltages above the 5-6 volt threshold of the Zener diodes. Whenever this threshold in the reverse bias is passed, they too start conducting a lot of current that can be limited only with an external resistor. However, the physics of this breakdown is different from the one of the Zener diodes and is in fact called avalanche effect, where the current is caused by a chain reaction inside the crystalline structure of the semiconductor. They too are used as voltage regulators, but for voltage higher than the one of the Zener diodes. LED or light emitting diode. LEDs are the well-known diodes used to generate light, either in the visible spectrum or the infrared or the ultraviolet. Depending on the color for which they are designed, they are made of different kinds of semiconductors, and as a result, they usually have different values of the forward voltage, which can range between 1.2 volts for infrared LEDs and 4 volts for white LEDs. Photodiodes. Photodiodes are used to detect light. The light acts as a source of energy to create holes and electron pairs in the lattice, thus allowing a current to flow when the diode is illuminated. Photodiodes are also used to produce electricity. In fact, solar panels are nothing else than arrays of photodiodes that are appropriately doped for this purpose. Varactor diode or varicap. Varactors are specifically designed to exploit the capacitance at the junction. Adjusting the bias of the diode allows to increase and decrease the size of the neutral region around the junction, causing the capacitance to increase and decrease between certain values. They are used whenever there is a need to control the value of a small capacitance with a voltage. We have gone through a lot of information today. Let's do a little recap to point out a few important things that you should keep in mind to efficiently use diodes. Number 1. Solid-state diodes are made of semiconductor material of type P and type N. Number 2. When we join together a P and N semiconductor, we obtain a PN junction, which has the characteristic of having a zone in the center totally deprived of movable charges. Number 3. The diode has two electrodes, the anode and the cathode. The cathode is the negative one and is the one that is usually indicated on the diode itself. Number 4. When we polarize the diode with the positive on the anode and the negative on the cathode, we say that the diode is forward biased and a current will flow through it, limited only by the resistance of the whole circuit. Number 5. When we polarize the diode with the negative on the anode and the positive on the cathode, we say that the diode is reverse biased. In such a condition, the diode does not allow the electric current to flow through it. However, if we increase the voltage above a certain threshold, that depends on how the semiconductor has been doped, the diode will suddenly start to allow the flow of the current, limited only, again, by the resistance of the whole circuit. This voltage threshold is usually very high, but certain diodes, like the Zener diodes, are built to have a low threshold on purpose, so they can be used as voltage regulators. And now you have it. You know enough on the diodes and how they work to have a better understanding of how circuits that contain them work. Thank you for following this video to the end, and please let me know through the comments if you find this kind of tutorials useful and if you would like to see more of them on other electronic components. Once again, if you liked this video and the channel, please subscribe and consider becoming a patron. Links for donations are in the description below. I'll see you in the next video, and in the meantime, happy experiments!